This is the first in a series of videos about studying stardust. This first video is just an introduction to the idea of what stardust is and why it's important. So let's start with thinking about the Big Bang. Assuming that we accept that the Big Bang is the origin of the universe, then a little under 14 billion years ago, the universe started. At that point, there was basically only energy. And then energy started to turn into matter. But very, very shortly after the start of the Big Bang, like 3 minutes after the beginning of the universe was comprised of just hydrogen and helium and a little bit of everything else. So lithium is the next one, but then a little bit of everything else, but basically so little that it doesn't count. Here you can see listed hydrogen, deuterium, tritium. Those are all isotopes of hydrogen. And helium-3 and helium-4 are isotopes of helium, and then lithium. At that point, the universe was expanding the whole time, and it had expanded so much and used so much energy that it was spread out enough and cool enough that no more nuclear fusion could happen. And so we couldn't stick hydrogens together to make anything else. And so we couldn't make any more heavy elements. At this point, approximately 75% of the universe was hydrogen. That's by mass. It's more like 93% if it's by number of atoms. If the universe started and it was mostly hydrogen and some helium and a little bit of other stuff, what does that mean for what we're made of or what our planet is made of? So what is the human body made of? Essentially, by mass, we're only 10% hydrogen. We're 60% oxygen, 20% carbon, 3 to 5% nitrogen, and there's actually a little bit of everything else in us. But except for the hydrogen, none of that existed at the beginning of the universe. So we have to make the oxygen, carbon, and nitrogen, and anything else that's in us that's not hydrogen or helium through some other means than the beginning of the universe. So where do those other elements come from? Well, they come from the insides of stars. And so I'm going to talk about the life cycle of stars and their dust. Here I have a star. This star is hopefully somewhat familiar. This is our sun. And in a few billion years, when it dies, it's going to start throwing material out into space. What you're looking at here is this is a planetary nebula. This kind of circular stuff that you can see here, that is a nebulosity. It's a cloud of dust, and it is reflecting light towards us. And this dust here is stardust. And this dust is made of elements that were already part of the star before it started to die, but it's also got materials that were made inside the star and are being thrown out. Now, this material heads off in all directions, and it meets up with material from other stars, and we end up with areas in the universe that have lots of dust. In fact, they have so much dust that we can't see through them. So this dark patch here isn't because there aren't any stars, but because the dust in them is blocking the light from behind, and so we can't see the stars through the dust. But these dust clouds are actually where stars get born. This is the Eagle Egg Nebula, and this is a very famous planet-forming region. In fact, each one of these little sticky out bits here, each one of those is going to become a star. So this is a huge cloud of dust that is collapsing from a cloud like this, and it is making new stars and planets and possibly life. So here we can see an example of a star that's forming. This one's in the Orion Nebula. In the middle, you've got the star that's almost a completely made star. And around it, this dark stuff, this is the dust again. This dust is what planets form from. Here we have an artist's conception of that. We've got a star in the middle, and we've got dust around the edges. And this dust is swirling around, and some of it's going to stick together. And the bits that stick together are going to become planets. And then the star in the middle is going to become a fully fledged star, and we're back at the sun. I just talked about what happens with dust coming off of stars and how we make those. But now I want to talk about where heavy elements come from. So we talked about how we need to make oxygen and nitrogen and carbon to make us. We also need to make silicon and magnesium and iron to make planets. And we want to know where they come from. So some stuff is made in the Big Bang. That's the helium and maybe a bit of lithium. A lot of it is made through exploding massive stars. This is what most people know about as stars that form dust, most people think of elements as being made in supernovae, and this is usually thought of as being exploding massive stars. Actually, there are other routes to making elements. For instance, we have cosmic ray fission. This is where larger elements get broken apart by being hit by heavy things. This is where we have two stars that are remnants of old stars, and they collide and have a big explosion. This is low mass stars when they're dying. And here where we have the exploding white dwarfs, that's where you have two low mass stars, but they are orbiting each other and their interaction causes an explosion. So we have lots of different routes to making heavy elements, and there's a separate video on exactly how all of that works. In fact, it's a video series. But let's look at where different elements are actually coming from. So you can see here, hydrogen is all from the Big Bang. Most of the helium is. But when we look at, say, lithium, actually most of the lithium is coming from low mass stars. So kind of like the sun. If we look at carbon and nitrogen, those are also coming from low mass stars. So the stuff that we need for life is mostly coming from low mass stars. But if we go to, say, silicon and magnesium, we can see that most of the magnesium is coming from high mass stars that go supernova. The silicon is a mixture of high mass stars that go supernova and low mass stars and binaries that go supernova. But if we go out to these much heavier elements, we can see that these heaviest elements are a mixture of low mass stars that are dying and this merging of two neutron stars. So elements are all coming from different places. Here, technetium is an element that doesn't have any stable nuclei, and so that's why it's in gray. This is where elements come from. Now let's talk about where the dust that some of these elements form, why that is important in space. And to do that, I want to take a terrestrial perspective. So here what I've got is what's known as the famous hockey stick curve of global temperatures. So this is basically a measure of how the Earth's temperature is changing from the year 1000 all the way up to 2000, where they're taking the average in the 60s to 1990, so around here, as being the 0 point. So what you can see is that for most of that time, yeah, it's wiggling about. You've got different temperatures for the planet all the way along. But as we get past the 60s and into the 2000s, what we're seeing is that the temperature of the Earth is rising rapidly, much more rapidly than these changes that we were saying before. Now, if we look at this in detail, again, we can see the wiggling around. So this is now 1950 to 2000. And there's this cooling that happened here. And this is due to the eruption of Mount Pinatubo. So Mount Pinatubo is a volcano in the Philippines. It erupted in 1991, and its eruption threw lots and lots of dust up into the atmosphere. So the ash that's coming out of an explosive volcano is made of lots of very small particles, similar to the sort of stuff we have in space, and it gets thrown up into the stratosphere. When it's up there, it's reflecting some of the sun's light. And in fact, it's reflecting enough light that so much light is stopped from getting down to the ground that that's what causes the Earth to cool. But it's not like we were in a nuclear winter or in a sandstorm. We didn't perceive there to be lots of dust up there. It wasn't hazy. It was just normal from the point of view of most people on the ground. So you didn't need to have a huge amount of dust up there in the atmosphere for it to have a huge effect on the energy flow, on how the light is passing through the system and causing heating. And so knowing about what dust is made of is really important for understanding its effect on different places in space. This is just another view of that same idea. So here we've got a more schematic version of it. Here's Mount Pinatubo, and you've got this drop that is happening because of Mount Pinatubo. But really what we care about is that all of this ash that's going up into the atmosphere changed the energy flow. Now we're way past the effect that had. However, we probably don't want to throw lots of dust up into the atmosphere. Anybody who has seen the movie or TV series Snowpiercer will know that the premise of that movie is that the Earth becomes too cold because of trying to use dust to reflect more sunlight, and that it went too far and we ended up too cold. Where is dust important? We're making all this dust, it's being thrown out into space, and it's going to be important for understanding all sorts of different things. First of all, we've got things like in the last 20 years or so, we've discovered a lot of exoplanets, that is planets around other stars, and understanding their formation. The dust is what is agglomerated into making new planets. We've got materials out in space where you get clumping, and that clumping is going to be something that is important for other different effects that can happen, like being able to do chemistry on dust grains. So if you've got a dust grain, you can use it as a catalyst. It can be the surface on which you have chemistry going on. And if it's clumpy, it's going to be high enough density that you're protecting all of these molecules from all the harsh radiation that's out there in space. And so the UV photons can't get to it, can't break up the molecules. So you can actually do complicated molecular chemistry on dust grains, and that's where dust grains become important. More controversially, one of the things that has come up in recent years is the idea of dark energy. Now, dark energy is so called because we don't know what it is. It's basically this idea that the universe is expanding faster than we expected it to be. Now, one of the things that is not well understood is how we correct for dust. When we do correcting our observations for dust, we assume that the dust is more or less the same, regardless of what direction we're looking in. But if we're looking a long way out into the universe, we're looking back in time, we may actually have completely different compositions of dust. Imagine that the first generation of stars made lots of silicon and magnesium because they were big, massive stars exploding. And so you'd have lots of dust that's made of those, but not much iron because you haven't made much yet. And so that's going to change the opacity, that is how much the light is blocked by the dust. And that's going to change the correction factors. Now, I'm not saying that dark energy isn't real. I'm saying we don't know whether the dust is going to make that effect even worse if we correct for it properly, or whether it will mitigate the problem. So dust is important in all sorts of different environments, and we need to understand all those different environments and what effect the dust has. Now, just to give you an inkling of the sort of things that are important in understanding dust and its interaction with light, because that's all we have when we're looking at stuff in space, let's imagine carbon. Carbon can be formed into all sorts of different forms that are called allotropes. The two most common ones are diamond and graphite. And we can see here, they interact with light quite differently. The graphite here is mostly black. It is absorbing most of the light that hits it, and what it doesn't absorb, it reflects. Whereas here we have diamond, it is transparent to visible light, and the light is passing straight through. So the interaction with light is different. So the effect on energy flow is different, and other dynamic effects that the dust can have will be different. We can go in further and talk about sapphires and rubies. Did you know that sapphires and rubies are in fact the same mineral? They are corundum. They are made of aluminum or aluminium oxide. But the difference is the impurities in them. The impurities in sapphires are iron and titanium. The impurities in rubies are chromium atoms. And those two different impurity systems mean that you have different colors. So clearly they are interacting with light differently, and that is not even down to their bulk composition, but the impurities that are embedded in the crystals. So let's come back to our life cycle of stardust again. Here's our sun. Here's the material it's throwing out into space. Here is the material being collected up with other dust from other stars. And here is the cloud collapsing. And here we have a planet forming system. And here we can see it at a different angle until we finally get back to having a star. So let's talk about what's going on here. We've got the light that is hitting the dust particles here. The light is actually absorbed and pushes the dust grains away. This is something called radiation pressure, which we'll get into later. Radiation pressure is something that causes material to be pushed. In fact, we're being pushed by light all the time. But if we apply Newton's second law, F equals ma, the force due to the light is very small, our mass is very large, so we really don't accelerate. But if you're a tiny little dust grain and you absorb a lot of light, then you will be pushed by that light. Similarly, when we get to having all of that dust that's being pushed out by light and it meeting with other dust and forming a big cloud, how well this collapses and how quickly it collapses depends on how fast it cools, and the efficiency of its cooling will depend on what the dust is made of. That dust then collapses down and starts to make a planetary disk, and you can get some turbulence in here, and that will also depend on what sort of materials are in the disk. So we really need to know what the dust is made of to understand all of the things that go on in these dusty environments in space. And there is dust in nearly every direction in space. This is a slightly more complex version of the same idea. So if we start from the interstellar medium here, so this would be a dark cloud, we've got stars forming, and it also forms planets. And so that's where we've got this planetary system. The stars, when they die, and we're going to get into this in a future video, when they die, they become red giants. They throw material back out into space. And so some of them just throw it straight back into space. Some of them become planetary nebulae and then throw stuff back into space. And some of them will explode as supernovae and leave behind some interesting corpses. But this is basically the system that we're interested in. And stardust is technically the material that is being thrown out by stars, whether it's a star that supernovas or just throws it out gently over time. And we'll be getting into that in more detail in our next video.